Okay, folks, for this video, I'm going to bring in the IGRF model, the International Geomagnetic Reference Model. I went on Google and typed in IGRF MATLAB, and this is the first thing that popped up. Somebody has already converted the standard Fortran subroutines for the IGRF model into MATLAB and made a bunch of different functions. And I'm actually glad that I'm doing this now because this was updated in December 2019. Or updated, I guess. It's hard to say. Yeah, it was created with 2007 MATLAB, so this was created a long time ago, and it was just recently updated. But anyway, if you click download, it will install, or not install, it will download a igrf.zip, and there's a bunch of different things in here. And there's probably this license. I just want to make sure I give credit to where credit is due. This is not my software. It looks like Drew Compston made this, copyrighted it in 2016. And it's provided by the copyright holders, and redistribution of the source code must retain the above copyright. So I'm not going to redistribute this code. I'm not going to push this to my repo. I'm just going to make sure that you understand. If you just Google this and in MathWorks, it'll pop up and you can download this. I am going to use this code though. So what I did was I loaded up this IGRF model, and I've already read the documentation, but I'm going to kind of go through what I did to learn how this code works. So it takes in time, latitude, longitude, altitude, and what's called the coordinate. And if you scroll down to the inputs, it says that time is a date field using the date num. So if I type in date, you'll see that it'll pop up like June 9th, 2020. So that's today, that's the day that I'm making this. So I could easily make my own date and say like 01 January 2000, and that would be my time. So I need to give it the time of day. The next one is latitude, longitude, altitude, and that's a pretty standard latitude, longitude, altitude for geocentric or geodetic latitudes and degrees. And then altitude, this is very important. This is the height above the Earth in kilometers. Okay, so we need to make sure that we send it in kilometers. Latitude and longitude needs to be in degrees. Coordinate then here is whether or not you want to use geocentric or geodetic, and it looks like geodetic is default. Now, if you scroll down in the code, what you'll actually see at the bottom, this is where everything is in a northeast down format, and then over here you've got convert to geodetic, and I actually want geocentric coordinates, and somewhere in this code here's the if chord geodetic. It does a bunch of stuff in here that basically converts the reference frames, and so what I want to make sure I do is in the main routine, what I first want to do is I want to set up the IGRF model. And so what I want to do is I want to create an IGRF setup, and then I'm going to make a new routine, and basically what I'm going to do is I'm going to make my chord, my IGRF chord is equal to, I want geocentric, okay, and then I also want to add path IGRF. And what that will do is that will add that IGRF path, and so I can make that call to that function. And then I'm going to call this IGRF setup.m. Okay, so now if I just clear CLC and close all, what I can do is I can test this. So I'm going to do IGRF setup. Okay, and then I'm going to run IGRF and see if it runs. And it looks like it does, it just says there are not enough input arguments. So now what I'm going to do is I'm going to give it a time. So I'm going to say 01 January 2000. I'm going to give it a latitude. So I'm going to say I'm on the equator in the prime meridian, and I am 400 kilometers above the Earth, and I want, and I'm going to do IGRF chord because that variable is defined. You can see here, it's in the workspace here. And then I'm going to hit enter. And then there you go, it outputs the magnetic field, and apparently this is in nanoteslas. And so if I type in bx, by, bz, and I hit enter, there is my magnetic field in nanoteslas. I can change the date to say 2010, and you'll see that they're pretty much the same. So if I want to convert from nanoteslas to teslas, I would just do bx equals bx times 1e minus 9. Nano is minus 9, and then there you go, there's bx in teslas. Now that does seem kind of large. Let me, I have this, I need to put this in here. I've got some documentation that I want to push to the repo. Let's see, documentation, spaceflight mechanics. Yeah, so I want to put this in here for you guys to have. I'll push this to the repo. And this is a sort of a text that I've created. And in here I've got a bunch of stuff, but I also have the magnetic field model. And here is an example magnetic field. And according to this, for a 56-degree orbit at 600 km, I'm supposed to have around 2e4 nanoteslas. And I'm getting like 3e18. So I feel like I'm calling the model incorrectly. Let me give it the defaults. That's interesting. If I do to default, I get exactly like 20,000 nanotesla. And actually, yeah, I get almost the same. I feel like I'm getting exact same numbers as here. Let's leave the IGRF out. And then actually, that means we don't really need this anymore because we really just need to add the path once. And so I'm just going to RM the IGRF setup. I don't need it anymore. Okay, so that means that we know how to run the code. Oh, and by the way, I did this last night. If you do like 2021, it will say that it's only valid between 1900 and 2020. And if you do, I didn't test the limit, but if you do June, all right, it'll still throw that error. Let me make this bigger here. If you do, let's try May. 01 May 2020. Nope. How about, so what about just January 2nd? Yeah, so you can only do January 1st, 2020. So we're going to have to pick an older day. But you'll notice that like the those parameters don't really change very much. So like if I go to 2020 versus 2000, I mean, you look at those parameters, you got like 2.0649 versus 2.066. I mean, you're talking about barely any change in parameters. All right, so in order to get the magnetic field going, what we need to do is we need to call the magnetic field model, and we can do that here. First, we need to compute the altitude above the Earth, or really what we need to do is we need to convert our Cartesian XYZ into lat, lon, altitude. And I'm trying to think where I want to do this. It looks like right here I call the planet, and then I also create our norm. I'm going to actually call this rho, and rho. And the reason why I want to do that is because in my spaceflight mechanics here, when I actually call, so this is a satellite. This red cube is in orbit, and there's an X, Y, and Z frame. That's an Earth-centered inertial frame, and you've got a psi angle, a theta angle, and then what I call rho, which is the distance from the centroid of the Earth to the cube. And so what I'm going to do is I'm going to use these equations here to convert from Cartesian to this latitude, longitude. So I've already got rho. Rho is just the norm. So let's see. Phi e is 0. Theta e is a cos of z over rho. Psi e is a tan of y over x. And then let's do a tan 2 on the off chance that x is 0. So we'll do a tan 2 y comma x. And then latitude, so latitude is just 90 minus theta e times 180 over pi. And then longitude is psi e times 180 over pi. And then the altitude is just rho minus r. And if you remember from the last video, r is defined in here in meters. Oh, and then actually that brings up a good point. We need to make sure that altitude is in kilometers. So we need to do rho divided by 1,000 to get to kilometers. So then we can get bx inertial, by inertial, bz inertial is equal to IGRF of, and I'm just going to pick a date. I'm going to say 01 January 2020 because that's the latest that I can do. And then I'm going to do latitude, longitude, altitude. And I think that's everything I need. I don't think I need this PDF anymore. And so it says that it's not being used, which is fine because we're not using it yet. But in order to plot it, what I need to do is I need to make bx, by, and bz. I need to make those globals. And then over in main, I need to make, I'm going to do a clear CLC and a close all. Initialize, that way I start with a clean slate. And then I'm going to make some globals, and I'm going to make global bx, oh yeah, it's bxi, byi, bzi. That's probably why the satellite routine gave me an issue. Okay, and then over here, what's going to happen is what I'm going to do is I'm going to simulate, and then what I'm going to do is I'm going to loop through state out to extract magnetic field. So I'm going to make bxi is 0 times state out of all comma 1. So that's just going to make a vector of zeros. And I'm going to call this out. Byi out is just bxi out. And then bzi out is bxi out. And again, so I'm just making dummy variables. And what I'm going to do is I'm going to say for idx equals 1 to length of t out. So I'm going to loop through my entire time vector. Okay? And now what I'm going to do is I'm just going to call the satellite dynamics. So I'm literally just going to grab this line of code and run it every loop, except instead of sending t, I'm going to send t out of idx and stay out of idx comma all. So that's going to send the ith row of state out. When I call that, every time it calls this routine, it's going to populate these 3 vectors. And since it populates those 3 vectors, now what I can do is I can say, all right, bxi out of idx is equal to bxi. And that variable exists because it's a global. And I can just copy this 3 times and then just change this to y and z, change that to y and z. And then finally, all I need to do is just plot it. So I can come down here, I plotted a 3D orbit. Let's plot the magnetic field now. And I'm going to do a fig2 is figure, and then set fig2 color white. I'm going to plot, and I'm going to do basically the same thing that I did in this thing here is I'm going to plot, I'm not going to do the percent orbit, I'm just going to do time, and I'm going to plot the magnetic field on the y-axis. So I'm going to do t out, bxi out, and blue, and I'm going to say legend, how does the legends work differently in MATLAB. So let's see, line width is 2, and then I'm just going to hold on, grid on, and then copy that twice, and do by and bz, and do a red and a green, and then actually let me make sure I get the colors right. So blue is x, green is y, so let's do green is y, and then this is, not z, z is red, this is green. And then I think I can do an x label time in seconds, and then y label. I didn't convert it, so this is going to be mag field in mag field nanotesla. Okay, and then I think, hopefully, nope, we got an error. Let's see, undefined function or variable z. So I think if I recall, yeah, I never actually, these were commented, I never actually extracted those out. So let's go ahead and pull those out. So now those are in the working memory. So now we can go back to main, hit F5, and sweet, we got it. And do we have two figures? We have two figures, there we go. And it does look different than, or sorry, this plot over here looks different than what I have here. And again, it's possible because I am in the wrong coordinate frame. I read a little bit more into what's going on here, and so what the system is doing is it's giving you northeast down, and northeast down is actually a function of where you are in the orbit. So like if you think about it, if you're on the prime meridian, north is this way, right, and east is that way. But if you're over here in like Mexico, north is still pointing in the same direction, but east is now pointing along the y-axis. And so what this is actually considered is like, if you look at this, there's no rotation about the x-axis. You know, there's a northeast down. The z-axis is pointing, you know, through the North Pole. And then, so if you look here, you know, when you want to go from these spherical coordinates to inertial coordinates, you need to multiply by this TIB matrix where you have phi e, which is always 0, you have theta e plus pi, and then psi e. Now this TIB matrix, this gets into some complicated three-dimensional dynamics that I haven't discussed. But if you recall in one of my videos, I was talking about Euler angles and how you do psi, theta, phi, where psi is along the yaw axis, theta is along the pitch, the y-axis, and then phi is along the roll axis. Well, you can actually put together this complicated rotation matrix here where TIB takes in phi, theta, and psi and creates this matrix here. So what I'm actually going to do is I'm going to code this matrix. And so I'm going to make a function called function TIB. I guess I'm going to call it out TIB, and I'm going to say phi, theta, psi. And I'm going to say out is, and I'm just going to code this big matrix here. And so it's going to be, let's see, cos theta. I'm going to make some variables here. Let's see, c theta, ct is cos theta. Let's see, st is sine theta. Let's see, s phi is sine theta, sine phi, and then c phi is cosine phi, and then s psi is sine of psi, and then c psi is cosine of psi. And so now I can do c theta times c psi, and then comma, and then say c phi times s theta times c psi theta. And then that's it. I'm going to call this TIB, throw it in there. And so now when I look at the satellite model, if I want to convert from, if I want BX inertial, or B inertial, first I need BNED, and that's going to be BXN, BY east, and then B, actually I could just do BN, B east, BD, so northeast down. So it's going to be B north, B east, B down. That's going to be a vector BED, and that's going to be TIB, and that's a function, and it's going to be phi e, theta e plus pi, and then psi e times BNED, and then I'm going to say BXI is BI of 1, BYI is BI of 2, and BZI is BI of 3. And so now if I run over here to main, of course it's going to throw an error, and it's going to say, something about, let's type in TIB of 0, 0, 0. I should get an identity. Let me move this out of the way. I should get an identity matrix. Oh, this needs to be, oops, this needs to be semicolons. My bad. That needs to be a column vector. Okay, let's try this again. Main. And okay, there's the system at, I actually changed some things in between videos, and so I actually didn't do the 56 degrees. So let's go back to the 56 degree inclination orbit. And whoa. Okay, folks, so I finally got it to work. I'm sorry for chopping this video so much, but I finally got it. If I run F5 here and run the simulation, looks like it takes a minute now to run. There's a lot of stuff going on in the background. There's my orbit. There's my magnetic field. This is the norm, and this is my position. So this is the position of the orbit. And this is the plot that I'm really most concerned about. And if I pull up my spaceflight mechanics, and then by the way, you're probably wondering, this model is using the C++ library. And so it's a little bit different. And then also this percent orbit is kind of misleading. And so I went ahead and so I have this exact same simulation in C++, and it uses a C++ library, which I've already validated. And so I ran it here, and you can see here's the planet-centered inertial, and they look identical. And if you look at the norm here, they look identical. And so this plot, in this one here, this is sort of misleading. It's the exact same plot. It's just a little bit skewed because the planet how am I trying to say this? Like the percentage of the orbit is calculated weird, and so it kind of scrunches and skews this plot a little bit, which sort of messes it up a little bit. But the good news is I ran the simulation with a if you recall in that last video with the IGRF model came from MATLAB, and Drew adapted it from Fortran. Well, I have the C version that was adapted from Fortran. But since I didn't do the conversion from Fortran to MATLAB, I was a little bit unsure of how it worked. So I dug into the documentation a little bit more, and what I found is that it will give you the northeast down component, but if you want to give it geocentric coordinates, the altitude needs to be from the radius of the center of the Earth. So what I actually had to do was, if you go here, when I run this model, I tell it that I'm giving it geocentric coordinates, not geodetic. I actually don't know what geodetic is, to be honest. But if you want to give it geocentric coordinates, the altitude has to be from the center of the Earth, not from the surface. And so now I was able to give it latitude, longitude, altitude, where altitude is not really altitude. This is more rho in kilometers, and this is more rho in kilometers. It's not really the altitude because it's from the center of the Earth. The other thing that I had to do to get this to work was that I realized that the northeast down is northeast and then down, which is towards the center of the Earth. And planet-centered inertial has down as up, right? So if you look at the diagram in the spaceflight mechanics, the z-axis is pointing up. And so when you do this rotation, you need to make sure that you negate the down component, and so that it goes into the correct direction. And then once you do that, you can run it, and then you get the exact same thing. So those are the only couple things that I changed in order for me to finally get the model that I was looking for. So I guess that's it. Hopefully this video chopping it all together wasn't too bad, and hopefully you'll enjoy the next part, which is on rotational dynamics, and I will see you then.